Sometimes we do see questions in JEE Advanced paper which are not very tough as such, but they genuinely probe your confidence level. They want to check how much confident you are in the results and formulae that you have learnt. Here is one such question. The question asks you to find magnetic field due to a current carrying loop at a point. The current loop consists of two concentric circular arcs of radii L and L plus delta L, where delta L is very small compared to L. This is a circular arc of radius L. This is a circular arc of radius L plus delta L. The arcs subtend a small angle at common center O. This angle is small. The other two segments of the loop are straight and radial. This is the current carrying loop we are talking about. These two segments are straight and they are radial. Magnetic dipole moment of this entire current loop. This is the current loop I am talking about. The magnetic dipole moment of this current loop is small m. It has a magnitude small m, and current in it is in anti-clockwise direction as shown in this diagram. Find the magnetic field at common center of curvature O. This radius is L. This is L plus delta L. Current is flowing like this. You have to write magnetic field at this point. The whole diagram is in the plane of the board. I am getting out of the screen for a moment. You can take the screenshot and try the question on your own. Solution to this problem is basically just a formula, and most of you know that formula, but it may or may not come directly into your mind. I will also pretend that I do not know that formula, or I am not able to recall that formula at this moment. So I will proceed in this manner. The question is pretty straightforward, and it can be solved using simple knowledge of Biot-Savart law. This is the loop that has been given to us, yellow colored loop, and this loop consists of two straight and two curved sections. Because of this straight section, there will be no field at O. Because of this straight section, there will be no field at O. But because of this current, there will be a magnetic field. Because of this current, there will be a magnetic field. And the vector sum of these two magnetic field is your answer basically. So let us assume that this angle is theta, it is small. This radius is L. So this arc length is actually L theta. And this arc length is actually L plus delta L into theta. So what we need to do is we need to write magnetic field due to this and add them vectorially. Let us do that. Because of this arc, the magnetic field will be inward. Either you know how to write magnetic field due to a circular arc, or you just know the Biot-Savart law. That will also work. Because this segment is nothing but a straight segment only. This angle is very small. So this is a straight current element having length L theta. It's very small because theta is small. And because of this, you are trying to write magnetic field at this point. Obviously, this angle between the current element and the position vector of point O with respect to current element, this is R in your Biot-Savart law, and this angle is 90 degree. So because of this current element, magnetic field here will be mu naught by 4 pi I into length of this arc, which is current element. You can take it as a straight element, sine 90 degree by this distance squared, which is L square. In this diagram, the magnetic field will be inward because of this arc. Let me take inward as positive direction. Because of this arc, it will be outward, so I am taking the difference. Because of this arc, writing in similar fashion gives I L plus delta L into theta. L plus delta L into theta is this arc length. So I dl sine 90 degree by L plus delta L whole square. Now, because delta L is too small compared to L, many students tend to write it as 0. Because you can neglect delta L in front of L. Here also you can neglect delta L in front of L, and therefore it becomes 0. No, that is not the way in which you should be doing approximations in physics questions. Something weighs 5,000.01 kg and something weighs 5,000 kg. if the question is asking you to find the difference in weight, then the answer is 0.01 kg. It cannot be 0. The question is asking you to find that difference. That difference is an absolute number. It is not being compared to anything else. Difference, you have to get the answer. But if somebody asks you to write this plus this, whether you write 10,000 or 10,000.01, it actually doesn't matter, isn't it? How much percentage error it is creating? Not much. So yes, when you are adding, you can write 10,000. But when you are taking difference, you shouldn't say 0, you have to say 0.01. So the difference between these two quantities is small. And that small quantity is what the question is asking you to calculate. You cannot just ignore it. So let us do the best possible approximation so that we get some difference. Don't take it as 0. Obviously, I can write it as mu naught I theta 4 pi, and here I am left with 1 by L. L cancels out, and here I am left with 1 by L plus delta L. Right. So now this can be further written as mu naught I theta 4 pi. You take LCM. In the numerator you will get delta L, and in the denominator you will get L into L plus delta L. Now L into L plus delta L, yes, it's fairly all right to write it as L square. 2 into 2.01, it's very close to 4. Error is there, but okay, we can afford to ignore that error. So this approximation is valid, but we shouldn't give our answer as 0. That is the point. Now in the question, I has not been given. Theta has not been given. In place of all that, the question talks about magnetic dipole moment of this loop. What is magnetic dipole moment of this loop? It is current into area. Current is I. What is area of this loop? Well, you can take it as a rectangular loop. In fact, it is very close to a rectangular loop because theta is small, these two are straight segments. What is this length? It is L delta theta, L theta, sorry, this length. What is this length? Delta L. So this quantity is directly given as M. So if I multiply here in numerator and denominator by L, I, L, delta L theta becomes M. So this becomes mu naught by 4 pi M by L cube. Oh. This is the formula I was talking about. Could you recall that? Okay, in 1 minute I'll get back to that. But let us first fix the direction. This is magnetic field due to this, which is in inward direction. So our answer has turned out to be positive, which means in this diagram the resultant field is in inward direction. What is the direction of magnetic dipole moment of this loop? Towards you. So in vector notation I can write that magnetic field at this point is mu naught by 4 pi M by L cube M with a negative sign, because the magnetic field points in a direction that is opposite to the direction of magnetic dipole moment of the loop, right? Now, I guess many of you will be like this. Oh, I was knowing this. Every current carrying loop behaves like a magnetic dipole. So what we have been given here is a small current loop, right? In fact, if it is a current loop and you are standing at a very far away distance, then from here it will look like a small loop only. So this is a small magnetic dipole. The magnetic dipole moment is towards you. This loop acts like a small bar magnet. And if there is a magnetic dipole like this, then this line is the perpendicular bisector of the dipole. And at a large distance L from this point, here the magnetic field is opposite to the magnetic dipole moment. The same result holds true for electric dipole also. If this is an electric dipole, let me represent it like this only. At this point, the electric field is directed opposite to the electric dipole moment vector. Similarly, if there is a magnetic dipole out here, magnetic dipole means it can be a bar magnet, it can be a current loop like this. Then magnetic field here will be inward, which is what we have got. And the formula for magnetic field at this point is the result that you have obtained, that is mu naught by 4 pi magnetic dipole moment divided by LQ. A similar formula is valid in case of electric dipole also. So if you know this concept that a current loop is just like a magnetic dipole, and the formula that you have learned for magnetic dipole can be applied here. Basically, you remember this formula for a large distance L, which is given in the question actually. This loop is small compared to L. So this formula can be directly used to answer the question. But how confident were you when you saw the question first? I, Sasi Bhushan Tiwari, promise to bring you some more interesting questions on this channel. Stay tuned, do subscribe. Goodbye.